In this video, we'll continue our discussion of the SVM optimization problem. In the last video, we looked at the primal optimization problem. We looked at what we have to minimize and the constraints, and then we mapped that to the inequality constraint that we need to use for solving the Lagrange. Now, continuing, we want to solve the dual version of the problem, right? And we know that from the KKT dual complementarity condition that alpha I, which is nothing but the Lagrange multipliers for the inequality conditions, right? So I is the training example. So there is one alpha I for each constraint. And note that here there are constraints for each training example. We want all the training examples to be outside the margin, either on the margin or away from the margin, right? And we know that alpha I gi is equal to 0. So that condition is what is the most important condition from the KKT conditions. So alpha I gi of w equal to 0. So we know that for the support vectors or the points on the margin. So I'm going to mark this up again just so we are clear which ones we are talking about. These points, the points on the margin. So the points on the margin are called the support vectors because for these points we know that gi of w is 0. So these are the margin, right? These are on the margin. So they satisfy that line equation, the margin line equation, which is this constraint here. So there is two parts to it. There is greater than 1 and less than 1, right? Sorry, greater than 1 and equal to 1. Right? So all points that are equal to 1 or this constraint in this constraint equal to 0 are the ones that are on the margin, the support vectors. So for those, gi of w is equal to 0. Hence, alpha I Lagrange multiplier can be greater than 0. But for all other ones, we know this is for the support vectors. For all other ones, all other data points, gi of w is less than 0. We know that, strictly less than 0. So it's not equal to 0, which means that alpha I should be equal to 0 for this product to be equal to 0. I'm reminding this multiple times in videos because this forms the basis of support vector machines. So the support vectors in support vector machines forms the basis, and that's what this is about. These points on the margin are the support vectors, and for the support vectors, gi of w is equal to 0, and only those alpha i's matter. So think about it. I mean, intuitively, when we want to place the line, we are considering where to place the line. Would this point in the far end, would this matter? Not really, because this is really far away from the line. Would this point matter? Not really, because this is really away from the line. But the points closer to the line, they matter. And that is the concept of support vectors and how to maximize the margin. I know I'm saying this more than one time in the videos. I just want to get this point across because this is really important and this forms the basis of SVMs. So just remember this. Okay, now let's continue. And we have the Lagrange now after we formulated the primal optimization problem. Now we have L, W, B, alpha, where W and B are parameters of the line equation, right? And alpha is the Lagrange multiplier, the vector. So all are vectors, so keep that in mind. W is a vector, alpha is a vector, here, and b is just one scalar we have for the line equation for the intercept. Only alpha i's here, no beta i's, because only inequality constraints are present in our problem. Now, we are trying to solve the dual version of the problem. Oops. And we have the Lagrange written out here. So I actually got a little too excited and I differentiated in the first equation. So the Lagrange is written out here. And we are going to differentiate this with respect to W, and then with respect to B, and set it equal to 0 to solve. So now first let's differentiate with respect to W. When we differentiate this with respect to W, then we go back to the first step. So this is the Lagrange, this is what we are going to differentiate. This one here, this is one. And then when we differentiate, we get this differentiation with respect to W. So we can see that this becomes half and 2W, so 2 cancels and we just get W here, right, this term. And then the second term, we have sigma I equal to 1 to m, data training data examples, alpha I, yi, w transpose xi plus b minus 1, right, this term. And when we differentiate with respect to W here, we only get the coefficient of W because we are differentiating with respect to this, right? So there are two terms here. Alpha I, yi, W transpose xi plus alpha I, yi, b, right? So, and then we also have minus alpha I for this one, right? There are three terms, and the only term that has W is this term. So when we differentiate, and it is a polynomial of degree 1, right? W transpose. So when you differentiate this, this is the vector notation, but it is just W, right? So it'll go away, and we just get the coefficient, which is alpha I, yi, xi, which is what we have here, right? Second term. And now we solve this equation. We differentiate, set it equal to 0, and solve for W. Then we get W. W is equal to sigma I equal to 1 to m alpha I, yi, xi, right? And then there's another term, B, right? We have to differentiate with respect to B and set it equal to 0. Now, there's only one term that contains B, right? So it is this term. This term here is the only term that contains B. And when we differentiate this and set it equal to 0, we get the coefficient of this term, coefficient of B in this term, alpha I, yi. There's a sigma in the front, don't forget that, right? So alpha sigma I equal to 1 to m alpha I, yi. So we get this, and then we get this is equal to 0. So when we differentiate with respect to B and set it equal to 0, we can't solve B because there is only a single polynomial of degree 1 for B, and when you differentiate it goes away. But instead you get a constraint. So this is a constraint, right? So we have sigma I equal to 1 to m alpha I, yi equal to 0. So we get another constraint. Now we can substitute both these values in the Lagrange. Now we have the Lagrange here written out in the last step of this page. And now what we will do is we'll substitute for W, and we'll substitute wherever we have alpha I, yi, we will sigma over alpha I, yi separately, we can substitute 0 for that. Now we have W square. We're going to write it out as W transpose W. Because remember, what is this? This is nothing but W1 square plus W2 square, so on, right? So that's nothing but W multiplied by W. And how do you write that in vector notation? Where you have W transpose, you transpose it and you multiply it with this. This is matrix multiplication, right? So because W is a vector, remember that. So now we have written out this quantity here as W transpose W. Great. Now we have the second term as it is. Now expanding, we are expanding into this guy here, this sigma. Now we have this minus and this minus cancel out. So we can get the first term here, sigma I equal to 1 to m alpha I, by multiplying alpha I with this minus 1 term in the last. So then we get this term. Okay, and we already have the second term is coming from the first term in the previous line, right? So we have these two sorted now. Okay, now this third term we are expanding this again. I'm going to erase this just so it's easy. Okay, so we have alpha I, yi, W transpose xi, right? That's one term when you multiply this out. And then you also have alpha I, yi, b sigma. This is another term. Now we got two things from our previous differentiating and setting that equal to 0. We got that sigma alpha I, yi is equal to 0. And b here is a constant. It's a scalar, it's a constant. So we can substitute that value here. And this entire term goes away, that's why. Because we know that sigma over alpha I, yi is equal to 0. By differentiating with respect to b and setting equal to 0, we solved and we got this, right? So we substitute that here. And then we are one term less. So then we go to the next step. So we get the first term as is, right? Now we take W transpose common in both these terms. In this term and this term we have W transpose, which is common. We take it out. Right? And then we have half W inside minus sigma I is equal to 1 to m alpha I, yi, xi. And we know that W, we solved for W earlier, right? We know that W is nothing but sigma I equal to 1 to m alpha I, yi, xi. That's what we got. When we differentiated with respect to W and set it equal to 0, we got this value. Now we substitute that here. Now we actually can see that both of these terms are the same, right? It's half of this minus the same term. So now we get minus half when we go through this. Now minus half of alpha I yi xi, right? And then the transpose of that. Now all that remains is W transpose. Now to understand W transpose, let's look at all the terms inside W transpose. So we know that W is equal to sigma I is equal to 1 to m alpha I yi xi. Now, which of these terms are scalars and which are vectors? Now, alpha is a vector, right? Alpha corresponds to all the Lagrange multiplier values for all training examples. Now, what about alpha I? So, alpha I is the Lagrange multiplier for the constraint corresponding to training example I, right? So it is the constraint, the coefficient of the constraint corresponding to the ith training example. Now alpha I is a scalar, right? So alpha I is just one value, so it's a scalar. What about yi? Yi is the class value, and we assumed a binary classification problem, and yi can take values either 0 or 1. So yi is also scalar. Now all that remains is xi. So xi is the feature vector corresponding to the ith training example. And we know that each training example can have more than one feature, right? Mostly we have multiple features corresponding to each training example. Now xi here is a vector. Right? Xi is a vector. Now, when we do a transpose, the only transpose that we need to apply here is on xi here. The other two values are scalar. So now, substituting that for W transpose, we get this entire term here. Now, we can see that there is a transpose applied on xi, and then there is also a version of x that does not have a transpose. Now we have two indices here, I and j, just to identify which is w and which is the transpose. So we have ij, and all the i's correspond to w, and j corresponds to the transpose, or it could be either way. It has the same meaning, right? So now we have this entire term that we get. Now we went to all this effort to solve the dual because we get this form, this form here, right here. So this, it can be written, so the xi transpose xj can be written as an inner product. So inner product is nothing but a generalized version of dot product, and you can see that mostly x is a vector, xi is a vector, so we will use the dot product version for vectors when we are considering this inner product. Mostly that's what we will be using, but it could be extended to other versions of x. That's why we call this an inner product. Now, this is why we went to all this pain of converting it to the dual and solving the dual optimization problem. Because the dual optimization problem is maximizing alpha over this term, where alpha I is greater than or equal to 0 and alpha I yi equal to 0. Remember, we got this constraint when we solved for b. We differentiated with respect to b and set it equal to 0. We got this constraint. Now, when we solve this form here, in this version of the problem where we solve it in this order, is when we get this inner product. So this inner product means that it's easy to switch out x and replace that with a function phi of x. And phi of x could be a transformation on x. Anything that transforms x into a more complex function. It's a function of x, right? So now we can just plug that in here in the inner product and it would still work. For many different kinds of functions, this is still true. And this right here, this green box that we have drawn around the inner product, that is called the kernel of SVM. And the kernel trick is when we replace this with phi of x and then make our SVM way more complex without changing our derivation too much. So we are not going to change our procedure. We are just going to swap this x with a function of x. For many functions, it would just seamlessly work. And that is the beauty of SVM. And if you are ever asked what is the kernel trick, it's not a simple answer, but all these derivation will point you in that direction, like why we need to solve it a specific way and what do we mean by the kernel and how the kernel helps us in extending SVM to more complex modeling scenarios. Phi of x can be Gaussian of x, can be a radial function. So these are different ways in which phi of x can just make our feature vector x way more interesting and give SVMs the ability to model complex problems.